is sponsored by Boot. Most modern AI products are built from the same set of core ideas. In the next 7 minutes, I'll walk through 9 concepts you will see repeatedly across real-world AI systems. 1. Tokenization. Neural networks like LLMs cannot work with raw text directly. A tokenizer breaks text into smaller units called tokens and maps each token to an integer ID. So the model can take the sequence as input instead of raw text. The most common algorithm is byte pair encoding or BPE. BPE starts from small units, often bytes or characters, and repeatedly merges the most frequent adjacent pairs to form new tokens. Over time, common fragments like ing or tion become single tokens. So words like walking might be split as walk plus ing. 2. Text decoding. An LLM simply outputs a probability distribution over the vocabulary for the next token. A decoding algorithm chooses one token from that distribution, appends it to the sequence, and repeats the process to produce a full response. The simplest text decoding approach is greedy decoding, which always picks the most likely next token. It can work well for deterministic tasks, but not for tasks requiring creativity. Sampling-based methods add controlled randomness to improve diversity. For example, top P sampling draws the next token from the smallest set of tokens whose probabilities sum to P, then samples from that set. 3. Prompt engineering. Vague prompts usually lead to vague answers. Prompt engineering is the practice of shaping instructions and context to steer a model's behavior without changing its weights. A strong prompt clearly states the task, key constraints, and the expected output format. One common technique is few-shot prompting, where you include a handful of examples so the model imitates the desired style and structure. Another is chain-of-thought prompting, which you ask for step-by-step reasoning. COT prompting can improve performance on problems that require multi-step logic like math and coding. Prompt engineering is widely used because it is fast to iterate on and inexpensive compared to training or fine-tuning a model. 4. Multi-step AI agents. An LLM on its own only generates text. It cannot take actions like browsing the web, checking the weather, or running code. Multi-step agents wrap an LLM in a loop with access to tools and memory. So it can plan what to do next, call external tools, and use the results to decide the next step. The agent repeats this cycle until it reaches the goal, runs out of a budget, or determines it cannot make further progress. 5. Retrieval augmented generation. A plain LLM answers using only what is stored in its weights, so it can be wrong or outdated on recent events or changing company policies. RAG pairs an LLM with a retrieval system connected to a knowledge store. When you ask a question, the retriever first pulls relevant passages from sources like PDFs, docs, or a database. Then the LLM uses those passages to write the answer. This grounds the response in external evidence instead of relying only on the model's memory. 6. Reinforcement learning from human feedback. The initial launch of ChatGPT succeeded in large because of the RLHF stage. RLHF is a reinforcement learning approach where the model practices by generating multiple candidate responses. A separate reward model scores them, and the training algorithm updates the model's weights. So higher scoring responses become more likely. Over time, this pushes the model toward outputs that people consistently rate as more helpful, clear, and safe, not just outputs that are statistically likely. RLHF aligns an LLM with human preferences mainly because of how the reward model is trained. The reward model learns directly from human feedback, usually from pairs of model responses to the same prompt where annotators pick the one they prefer. By learning these preference patterns, the reward model becomes a proxy for what humans tend to want. And reinforcement learning uses that signal to steer the LLM toward responses that score higher on that proxy. 7. Variational autoencoder. A VAE is a generative modeling approach that learns a probability distribution of data. A VAE consists of 2 neural networks, an encoder and a decoder. The encoder maps the input into a low-dimensional latent representation, while the decoder maps the latent vector back to the original input space. Training optimizes a reconstruction objective, so the decoded output stays close to the original input. After training, new data can be generated by sampling a point from the latent space and decoding it. In modern text-to-image and text-to-video systems like OpenAI's Sora, a VAE is often used as a latent compressor, allowing the downstream model to operate more efficiently in a smaller space. 8. Diffusion models. Diffusion models generate data by learning to reverse a gradual noising process. During training, you take real samples, like images, add noise over many time steps, and train a model to predict the noise given the noisy input, the time step, and optional conditioning such as text. At inference time, you start from pure noise and repeatedly apply the learn denoising step to move toward a clean sample. 9. Low-rank adaptation. Large models like LLMs and text-to-image systems are general purpose. They handle broad everyday tasks well, but often struggle in specialized domains. LoRa is an efficient fine-tuning method that adapts a pre-trained model without updating all of its parameters. It keeps the original linear layer weights frozen and adds two small low-rank trainable matrices. AI labs like OpenAI and Google spent years perfecting LLMs, but the real breakthrough happening right now isn't better LLMs, but a shift from talking to doing. So what turns a powerful LLM into something that can actually research, book flights, write code, or manage your entire project? AI agents. Here's the difference between an LLM and an AI agent. LLMs are neural networks trained on internet data. They are great at predicting text, answering questions, and explaining concepts, but they have clear limits. For example, if you ask, what is the weather in San Francisco today? A plain LLM does not have today's live data. It might confidently guess, but it isn't actually checking anything. Or if you ask it to research AI trends with citations, it cannot reliably search the web or verify sources. It is just generating text. Think of the LLM as a human brain. A brain can reason and plan, but it cannot directly interact with the outside world. It can't open a browser or send an email. Humans become powerful because the brain coordinates with hands, eyes, and external tools. An AI agent wraps an LLM with three specific components: tools to act, memory to remember, and a reasoning loop to get the task done. It is not a new model, but software that orchestrates this system, allowing the LLM to provide more value than just generating tokens. Let's look into each component, starting with tools. Tools are external capabilities the LLM accesses whenever it needs extra information or wants to take action. These tools can be simple Python functions like a calculator or external APIs like search, booking, and internal company services. Each tool is defined by a schema telling the LLM what inputs it expects. When the LLM needs a tool, it outputs a structured call, showing which function or API to use and with what arguments. The agent's orchestrator runs the function and feeds the result back to the LLM. For example, if you ask, what is 17 times 24? The LLM recognizes it needs a calculator. It outputs a specific tool call with the arguments 17 and 24. The agent's orchestrator executes this function, receives 408, and feeds it back to the model so it can answer 17 times 24 is 408. Or consider a request like book dinner for 2 tomorrow at 7 p.m. in San Francisco. The LLM asks for a web search to find restaurants. The agent calls the search tool and feeds the results back to the LLM. Then the LLM asks to book a specific place, and the agent calls a booking API with the restaurant time and party size. The LLM receives the result back and outputs a confirmation. The second key component is memory. If the LLM is the processor, memory is the hard drive. There are two kinds of memory in an AI agent: short-term memory and long-term memory. Short-term memory is the LLM's context window. This is everything the model can see in the current conversation and the current working state. Short-term memory is great for keeping track of what the user just said, what the agent just tried, and the immediate plan, but it is limited by the context length. Long-term memory involves storing information outside the LLM and then retrieving it when needed. The agent can store user preferences, previous tasks, notes from earlier conversations, or company documents. When a new question comes in, the agent retrieves relevant info and pulls it into the context. For example, if you travel often, the agent stores your past conversations, which indicate you prefer aisle seats and direct flights. A month later, when you ask for a new trip, it retrieves those preferences from the long-term memory into the context window to plan accordingly. The most critical part is the reasoning loop. Instead of the LLM being a one-shot chatbot, this loop turns an LLM into an agent by placing it within a continuous cycle. Here is how the loop works. The LLM processes the context and thinks about the task, decides which action to run, produces the tool call, and the agent feeds the outcome back to the LLM. Instead of stopping here, the LLM reasons again. It iterates until it reaches a goal or decides it cannot proceed. A common pattern is REACT, a prompting technique that instructs the model to follow the strict thought action observation format. Imagine you ask, find a United flight to New York next Friday under $300. The agent enters a loop to process this. It starts with a thought. I first need to check what date next Friday is. The LLM requests an action by outputting calendar tool. The agent runs the function and sends the result back as observation. Next Friday is October 18th. The LLM takes that observation and loops again with a new thought. Now I can search for flights. It produces a call to the flight API tool with the date and price limit. The agent returns a list of flights as observations. Finally, the LLM concludes, found United Flight 294 for $280 departing at 10 a.m., and returns the final answer. This reasoning loop makes agents reliable. If a tool fails, the agent retries. If the request is unclear, it asks a question rather than guessing. In short, an AI agent is just a looping system built around an LLM with access to tools and memory. It reasons about a goal, plans next steps, uses the right tools, and remembers its progress to get the job done.
Two protocols, two tech giants. One version that's going to shape how every AI agent on the planet talks to the outside world. In November 2024, Anthropic dropped MCP. 6 months later, it had become the standard. OpenAI adopted it, Google said they'd support it, thousands of developers built integrations. Then in April 2025, Google announced A2A, with 50 partners already signed up. Salesforce, MongoDB, SAP, PayPal, and they did something interesting. They said A2A complements MCP, not competes, complements. But the internet wasn't buying it. Solomon Hykes, the creator of Docker, tweeted, in theory, they can coexist. In practice, I foresee a tug of war. So what's actually going on? Is Google playing nice, or did they just fire the first shot in an AI protocol war? Let's break it down. You are a developer, you have built an AI assistant for your company. It's smart, it's helpful, but it's also completely blind. It doesn't know what's in your Slack, it can't see your Google Drive, it has no idea what's in your database or your CRM or your GitHub repos. Every time a user asks about something company specific, the AI just guesses or apologizes. So you start building integrations. You write code to connect your AI to Slack, then Google Drive, then Salesforce, then your internal wiki. Each integration takes weeks. Each one has its own authentication flow, its own data format, its own error handling. Think about what USB did for hardware. Before USB, every device had its own proprietary cable. Your printer, your keyboard, your camera, your phone, all different connectors. USB said, here is one standard plug. Build to this, and everything works with everything. And that's the promise of MCP, the USB-C port for AI. Say you want Cloud to access your company's PostgreSQL database. Without MCP, you're writing custom code, database connectors, query builders, result formatters, error handlers. With MCP, you spin up an MCP server, which is basically a lightweight wrapper that exposes your database through a standard interface. The MCP server publishes three things. First, resources. These are data the AI can read. Your database tables, your schemas, maybe some sample queries. Second, Prompts, templates that help the AI interact with your data effectively. And third, tools, functions the AI can actually call. Run this query, insert this record, update this row. Any MCP compatible AI can now access your database. And any MCP server you add to your setup, say for Slack or GitHub, automatically becomes available to all your AI applications. And this is why MCP exploded. Within months of launch, the community had built MCP servers for Google Drive, Slack, GitHub, Notion, Postgres Drive, and hundreds more. MCP was the standard. So why would Google launch something different? Google's argument is that MCP solves only half the problem. It handles what they call vertical integration, connecting an AI to the tools and data beneath it. But what about horizontal integration? What happens when you have multiple AI agents that need to work together? Let me give you a scenario that makes this concrete. You are an enterprise. You have got a customer service AI that handles support tickets. You have got a separate AI that manages your knowledge base. A third one handles billing questions. A fourth does technical troubleshooting. Each of these agents is good at its specialty and uses MCP to connect to its relevant tools. A customer writes in, I was charged twice for my subscription and now I can't log into my account. This ticket touches billing, authentication, and possibly technical issues. No single agent can handle it. The customer service agent needs to ask the billing agent to check for duplicate charges. If there is an account issue, it needs to loop in the authentication agent. If there is a bug, maybe the technical agent needs to investigate. How do these agents coordinate? How does this customer service agent know what the billing agent can do? And how they pass context back and forth? How do they handle a resolution process that might take hours or days with a customer checking in periodically? MCP doesn't have answer for this. It's designed for agent to tool communication, not agent to agent collaboration. And that's the gap A2A fills. A2A introduces some concepts that are genuinely clever. The first is the agent card. Every A2A compatible agent publishes a JSON file at a well known URL, typically /.wellknown /agent.json. This card describes everything another agent needs to know. What skills does the agent have? What authentication does it require? What kind of task it can handle? And how should you communicate with it? Think of it like a LinkedIn profile for AI agents. When agents need to collaborate, they first discover each other by reading these cards. The customer service agent finds the billing agent's card, sees that it can handle refund requests, and now knows exactly how to ask for help. The second concept is the task lifecycle. When one agent asks another to do something, that request becomes a task with a unique ID. And unlike a simple API call, this task has states: submitted, working, input required, completed, failed. The task can take minutes or weeks. Agents can check in on progress. They can provide additional information when needed. They can handle interruptions and resumptions. This matters because real world business processes aren't instantaneous. That duplicate billing issue, maybe it requires a human in finance to approve the refund. Maybe it needs an investigation that takes a few days. A2A is designed for this kind of long running multi step collaboration. Google has also built A2A with enterprise security from day one. Agent cards specify authentication requirements. The protocol supports OAuth, API keys, and can integrate with existing identity providers. This wasn't an afterthought, it was a core design principle. Now, Google has this analogy they use, and I actually think it's pretty good, so let me extend it. Imagine an auto repair shop run entirely by AI agents. You have got a shop manager who talks to customer, you have got mechanic agents who do the actual repairs, and you have got supplier agents who provide parts. When a customer walks in and says, Hey, my car is making a weird rattling noise, that's an A2A conversation. The manager needs to ask follow up questions, maybe request a video of the noise, understand when it happens. This is conversational, fuzzy, multi turn. The manager figures out it's probably a suspension issue and hands it to the mechanic agent. That's another A2A interaction. Task assignment between agents. Now the mechanic needs to actually diagnose the car. They use a diagnostic scanner. That's an MCP tool call. They check the repair manual database. Another MCP call. They raise the lift to inspect underneath. MCP again. These are structured, precise interactions with specific tools. The mechanic discovers a worn bushing and needs to order a part. Now they are talking to the supplier agent. Back to A2A. Do you have the part in stock? When can you deliver? What's the price? This might involve negotiation, back orders, and alternative parts. The distinction is clear. MCP is how agents use tools. A2A is how agents talk to each other. One is structured and synchronous, the other is conversational and potentially asynchronous. But here is where it gets complicated. What happens when the line between tools and agent blurs? Think about a modern search engine with AI capabilities. Is that a tool or an agent? It takes natural language queries, reasons about intent, synthesizes answers from multiple sources, can handle follow up questions. It has agent like properties, but it's also something other agents invoke to get information. Or consider a code review system. It analyzes pull requests, explains its reasoning, responds to developer questions, can be asked to focus on specific concerns. Tool or agent? The honest answer is it's both, depending on how you are using it. And this is where the complementary framing starts to feel less clean. If the same system can be both a tool and an agent, what protocol do you use? Do you implement both? Do you translate between them? Developers are already feeling this tension. Building for one protocol takes significant investment. Building for two takes more than twice as long because you are maintaining two integration patterns, two auth flows, two ways of thinking about your system. In practice, teams pick one and optimize for it. AI agents are getting powerful very fast. They can read GitHub PRs, post messages to Slack, create issues, query databases, even send emails. Most of these agents work perfectly on your laptop, but completely fall apart the moment you try to deploy them for a team. And the reason is not AI, it's authentication. You probably know that MCP or Model Context Protocol is Anthropic's open standard for connecting AI systems to external tools like GitHub, Slack, Gmail, and databases. Instead of writing custom integrations for every service, MCP gives you a standardized way to expose tools that any AI agent can call. So when your MCP server talks to GitHub, it uses your token. When it posts to Slack, it posts as you. That works fine for demos. But the moment you want to deploy this for a team, you hit a wall. You cannot hardcode your GitHub token. You cannot share Slack credentials. And you cannot safely run an automation that acts on behalf of multiple users without knowing who authorized what. This is exactly the problem the sponsor of this segment, Arcade, solves. Instead of your MCP server owing credentials, Arcade manages OAuth for each user. Your MCP server never stores secrets. It simply requests actions, and Arcade executes them securely. And this is not a workaround. In fact, Arcade directly contributed to the MCP specification that enables secure tool level authorization in MCP. And to make this concrete, we built a real automation using Arcade MCP. Whenever someone opens a pull request in a GitHub repository, a notification is automatically sent to a Slack channel with full PR details. At a high level, the system looks like this. A pull request is opened on GitHub. GitHub Actions triggers a workflow. The workflow runs a Python script. That script talks to Arcade MCP. Arcade securely calls GitHub to fetch PR details and Slack to send the message. No tokens are hard coded, no credentials are leaked. Everything runs with scope pre authorized access. And this is the difference between a demo and a production system. We defined two core files. First, Slack notify YAML. Its job is simple trigger on every pull request. All you need to do is set up Python, install Arcade Py, and run the trigger script. This workflow contains no credentials, it only provides execution context. This script uses two Arcade MCP tools github.getPullRequest and slack.sendMessage. First, it fetches PR details from GitHub, then it formats a structured Slack message, and finally, it sends that message to the configured Slack channel. Everything flows through Arcade's MCP layer. Once GitHub and Slack are authorized in Arcade, this runs automatically on every PR. Huge thanks to Arcade for sponsoring this project and supporting real world MCP workflows. All links and the full project repository are in the description. Building an MCP server locally is easy. Running it for a team is where reality hits. Now you need SSO, audit logs, token refresh, multi tenancy. MCP is still evolving on auth. A2A is stronger there, but has a smaller ecosystem. The simple takeaway is use MCP today for tool integration, learn A2A for multi agent setups, and expect real systems to use both. Both will likely converge as tools and agents blur together. And if this was useful, do subscribe and I'll see you in the next one. According to Stack Overflow's 2025 developer survey, 87% developers worry about the correctness of AI generated code. And that's almost everyone. 66% said their biggest complaint is code that's almost right but not quite, close enough to look good, and wrong enough to break in production. So we have a problem. AI can write code faster than ever, but we can't trust it. What if there was a way to fix this? Not with better prompts, not with bigger models, but with a completely different architecture. What if instead of asking one AI to generate code and hoping it's correct, you made multiple AIs compete against each other and let another AI pick the winner? That's exactly what Atoms built with something called race mode. And the system design behind it is fascinating. This video will break down how race mode works, the multi-agent architecture, the parallel execution, the evaluation system. We'll look at the distributed system patterns that make it possible. And I'll show you a live demo. This video is sponsored by Atoms. Let's get into it. To understand why race mode exists, we need to understand why single agent AI coding fails. When you ask ChatGPT to write code, it generates tokens one by one. Each token is a prediction, and along the way, it's making thousands of decisions. Which framework, how to structure things, what edge cases to handle. Each decision is a fork in the road. The model picks
Sorry.